What is the situation for me now, engineers? I have a bus bar like this, and one of the feeders on this bus bar is my capacitor bank feeder. It is simply there, coming out like this, and it goes to the capacitor bank. All right? I will draw it for you here. But it is, of course, three-phase. Very good. So, what is the situation, engineers? What is the purpose of this capacitor? Bank? Look, engineers, if you have a generator, I will explain it simply for you to understand. It's not our main topic, but I'll explain it simply for you to understand. And here you have a load. All right, very good. This generator produces S, which is the apparent power in volt amperes. Consequently, this load also draws S, which consists of P plus JQ, correct? The P comes from any resistive load, and the Q comes from any inductive or capacitive load. The conductive or capacitive load, all right, very good. In the end, you have the impedance of the load, which is R plus GXL minus GXC. These are responsible for drawing what? For drawing the reactive power, and this is responsible for drawing what? The active power. So this is what draws the P, which is called active power, right? And these are what will draw the Q, which is the reactive power, right? But there is a difference between the two. This one draws reactive power, whereas this one gives you reactive power, all right? This is called active power. And this is called reactive power. What does that mean, engineer? If you have a load like a motor, the active power that the motor draws is the power responsible for moving the motor. It is the power that is converted from electrical form to mechanical form or kinetic energy. Reactive power is the power that is involuntarily drawn in the form of the magnetic field that transfers from the stator to the rotor to create mechanical movement. It is solely for the process of magnetization, or what we refer to as our field or magnetic field. All right, so now engineer, you have this generator that produces B and B produce Q, add E, B and Q, okay? Or B and Q like this, add E. Q what? All right, great, and here's your total S. This is P and this is Q, and here's the total S. This S is constant, meaning this generator produces a constant S. Let me draw something like a circle around it, and this is your center, all right? So the S is constant. Now, what matters to me is that the more Q decreases, like reaching up to here, I can reach more P. So here's P, and if I reduce Q to here, I can reach P. Or like Q here, I can reach this point because it's the same S. The S has moved along this semicircle. So if you reduce Q by this amount, you've increased P by this amount. This is what concerns me. This P is what I want. This is what I will provide to the consumer. This is what everyone wants for lighting, motors, air conditioners. Any loads running at your place need P. This is what's important to me. This is what I will charge for. This is my power. You might say, but engineer, you can also charge me for Q. Not everything is about money. But if I charge you for Q, if my generator produces 100 MVA with 50P and 50Q, I will charge for them. Yes, but those 50P, the 50 MVA of power, will only be useful for 3 or 4 subscribers, for example. All right, why? Because in essence, if I draw power, I can't provide it to other subscribers, even if I withdraw my money from the Q. This means I have to build many power stations to supply all my loads, right or wrong? You said right. Okay, this Q that is drawn downwards is due to the inductive load. The inductive load is any load in coils, like the motors found in air conditioning systems. All right, like the air conditioners found in factories, exactly like those in factories, and like those in lighting. Lighting is also considered an inductive load. Anything with a coil is considered an inductive load to me, and it draws Q. All right. The capacitor provides Q, so here we can say this is QL and this is QC. All right. The capacitor provides Q. All right. So what will I do if I place a capacitor here that provides Q? instead of having all of this as my Q, when I add a part QC, this part is subtracted from that part, leaving me with only this portion. And if I increase QC even more, I might reach a point where I don't have any QL at all, and all my S is converted to what? It's converted to power. So if I reach a point where the capacitive reactance equals the inductive reactance, these two cancel each other out, leaving me with just this, and I have obtained additional power. This is the goal of the power factor correction concept, which is improving what? Improving the power factor, right? Very good. Well, I don't want just that. I am not introducing the capacitor bank just to achieve power factor improvement. So what else do you want, Engineer Rashad? Well, as a result of drawing this Q engineers, what happens is you get an voltage. Why? Because very large currents are drawn in this reactive power. Large currents are drawn, which are the reactive current, leading to under voltage. So if I introduce the capacitor bank into service, the capacitor bank provides Q, and Q is not drawn from the generator. So you have another source providing Q, not the generator. Who would be the capacitor bank? And thus I reduced the Q from the generator, and thus reduced what I reduced, or reduced the active power drawn from the generator, and thus the quality returned. And I started to have under voltage, and the voltage returned again. What in a healthy way is good, like this? Bashman Sat, good before. Okay, the capacitor bank has a controller panel called ACCS, which is, what is it? Which is automatic, which stands for automatic. Capacitor, exactly. Control switch, yes, switching, exactly. Which is something that automatically controls the opening or closing of the breaker to connect or disconnect the capacitor. This control is done based on two measurements, either the voltage measurement or the megavar measurement, which is the reactive, yes, reactive power. It measures the amount of megavar coming from the transformer incomer. Of course, for me, this is my source. So it measures the amount of megavar, and if it finds it drawn above a certain limit or exceeding a certain limit, it automatically connects the capacitor bank in this breaker to supply the reactive power. This way, the reactive power drawn from the transformer becomes slightly less, and the quality here returns to being correct. Or it measures the voltage present here on the bus bar. If it finds it low, it connects the capacitor bank, because this means it decreased due to an increase in active power. So it compensates for this again. This is the idea of the capacitor bank I have. All right, let me close this now and get back to you. All right, so you'll find here what I was telling you about, that the capacitor bank or automatic capacitor control switch can close the breaker, but it is only necessary in the service position. So you'll find here the service position. What is this, engineer? Who is Keto? I have here LS4 and LS6. I went to the breaker page and found out they are test service, but how are you telling me that Keto is for what? It is for the service position. How did you know that Keto is something related to this? Well, look, engineer, this is obviously a mistake by the person who was working with you. Here, in the schematic diagram, it should have been mentioned underneath. If you follow here, engineers, it should tell you the page number, which is, here, like this. I want to come here to my drawing. If I come here like this, engineers, here it is. Here is K2. It was supposed to tell me, engineers, where K2 is coming from. So now, of course, I will show you. You walk like this, keep walking, walking until you reach where K2 is. So, of course, this should be page 20, and K2 is located in 4. So it was supposed that on the previous page there, it would say that this contact source is page 20, A4. It should write below it like this, 20, A4. Good. So what's going to happen, engineer? What's going to happen is that you will come here. This is your indicator. Okay, you will find it consists of an auxiliary coming here, negative, and it still needs a positive coming from above, taking contact from where? From LS7, from the dotted box here. So this is coming from the breaker, and this is the breaker. Its symbol is Q0. This is the symbol for the circuit breaker, and LVB is the voltage plug, which is the low voltage block. Low voltage block gradually, indicating it's coming from something inside my panel. This is the low voltage block to avoid overload. Now you know the low voltage block. Q0 is the number of the breaker. And the name of the breaker you have all right. Very good. So if I go to the last page and look for where LS7 is, I'll find that LS7 says it's a position switch close in run position, meaning it should be closed in the service position. So if I come back here again, it tells me the following. It means if the breaker is in the service position, this contact is closed. Is it closed in this? So why does the auxiliary operate? And based on what? Since I am using a normally open contact here, it means when the breaker is in the service position, the auxiliary will operate and close its contact here. So this means what? It means it is in the service position. Well, patience, why didn't I just put LS7 directly here? Here. This is another function we call contact multiplication. What does contact multiplication mean? It means I have two limit switches, but they handle the service position state. Suppose I now want to operate a lamp to indicate that the breaker is in the service position. If I had used LS6 here and LS7 there, I wouldn't have been able to know the information, or rather, I wouldn't have been able to get another contact to operate this lamp. So I did something called contact multiplication, meaning I will create multiple copies. So here the engineer does what? He starts by taking one of the limit switches to operate an auxiliary. What is this auxiliary? It has more than one contact. So in this way, engineer, let me show you like this. This is our approximation protection, meaning what does the sensor do? It comes here like this, takes the DC positive and negative, takes here like this. This is the limit switch, which is number 7. It operates the relay XOR. This is, of course, a coil. And this coil has a contact normally 2, 3, 4. So when this closes, this one operates, and then it closes, 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 closes. So all of these have closed when this one closes, right or wrong. So it's as if I have turned this into 4 copies, each one used in a different circuit. We call this contact multiplication. Contact multiplication means creating copies of the same operation method of this limit switch. All right, engineers, very good, beautiful. So this is our story with contact multiplication. Okay, so this is the ACS. Okay, and these, Engineer Bashad, you told us you would explain them. Let's take the first one. T1. What is T1, guys? It's a timer. All right, and where is this timer coming from, Engineer Bashad? Or you don't know where it's from? It's coming from page 20, section 8, right? I'll go to page 20, section 8, and proceed like this. Which page is this? Here it is, page 20. Where is section 8, Engineer Rashad? Here is section 8. This is it, Engineer Rashad? Very good. Do you see this indicator? Where is this indicator? Here it is. It's called a timer relay. What's the story with this timer, Engineer Rashad? It's very simple. Come, this timer, what's up with it? This timer is here on page 20, the same page, section 3. Here is section 3. Valley 3, my timer valley remains here. Where does this timer work from? From Q0. I will go to the last page. I will discover that this contact is the circuit breaker state. When the breaker is open, this timer works. What does this mean, my dear Bashons? Praise be to God, it is very simple. Focus with me. What does this timer mean? Let me go back here like this. And let's do an approximation here like this. Okay, and I start to enlarge the area or the page like this. Okay, this timer that we're talking about here, what does it mean? Look, engineer, you have this timer, we call it the on delay timer. The on delay timer, nice, very nice. What does on delay timer mean, engineer? This timer is like the same coil with a set of switches, okay? Like normal open and normal close. Okay, what is this timer? If you apply a 125 volt DC supply to it, okay, very nice. This is the supply you put on this coil. Okay, as soon as you apply the supply, does it change the contact positions? No. What does it do? It counts a delay time. This is an on delay, meaning it is on, but after a delay time. Okay, meaning a delay period. It stays without engaging the supply. It waits for a period, and then it changes its contact positions and starts working. So as soon as you apply 125 volts DC, it first counts the time. 1 second, 2 seconds, 3 seconds, depending on the setting you have configured it to. Then what does it do? It changes its contact positions, turning the normally open to closed and the normally closed to open. Okay, there you go. Sorry. Certainly what I did was create a duplicate similar to this example, which we can refer to as on-delay timer. This can be applied to any of the shapes available. Allow me to demonstrate by selecting any one of these shapes for you. By doing so, I can show you how each shape can be utilized in this context, ensuring you understand the process thoroughly. Any of these shapes, and you have a knob here that you start to adjust, turning it to a specific number of seconds or minutes as you wish. And as you can see here from the diagram he drew for you, it's the same as what I drew. This is the timer coil. So this is the timer coil. Here is the timer coil, which is this file. You apply the supply to it at a certain moment, and here is the timer contact. So this is the timer, the contact, which is the timer's contacts. So when you applied the supply to the coil, what did it do? It first waited for a period of time and then changed the state of the contact. And when you remove the supply from it at any moment, the contact resets immediately at the same moment. So it only has a delay at the moment of turning on, but at the moment of turning off, it resets instantaneously. All right, so this is the story of the on-delay timer, okay? Engineer Rashad, when does this operate? It operates from the state of the breaker being open. As soon as the breaker opens, this timer starts. So what does that mean, Engineer Rashad? Let's see what this means. Here in our diagram, it tells you that this contact is normally open, right? Great. So as soon as the breaker opens, this timer counts seconds and then closes this contact. As soon as the breaker closes, the timer resets and this contact opens again. When does it close again? As soon as the breaker opens. So what does this mean? What do you want to do as soon as the breaker opens? Don't close this contact immediately. I want to wait for a period first and then close this contact. Why is that, engineer? Because this is a capacitor. When it was operating, it stored electrical charges inside. This is a capacitor and its voltage is high, right or wrong? Now you've disconnected the circuit breaker. If you reconnect it, the capacitor has voltage and the bus bar has voltage. Closing both together will cause a large arc on your circuit breaker. So he wants to ensure that from the moment the circuit breaker is opened, a certain amount of time is waited. This time is recommended or provided by the manufacturer of the capacitor bank. It tells you not to close the capacitor before, for example, 1 or 2 minutes have passed. Do not close the breaker again before, for example, 1 or 2 minutes have passed. Why, engineer? Because the capacitor needs to start discharging its charge into its internal resistance a bit first before closing the circuit breaker again to prevent any arcing at the moment of closing the circuit breaker. So this contact is operated by a timer, as we have seen, and the timer is activated by something like the breaker being open. As soon as the breaker is open, the timer starts counting time, and then it closes this contact to allow you to proceed. To close what? To close your breaker. Sorry, engineer, I think there's something on my screen. What next? So it allows you to close your circuit breaker once again. Is that clear, engineer? Great, my friend. We have now completed the closed circuit entirely without any missing parts.